Yes, can you hear me?
Yes, sir.
Okay. So we're waiting for Nobo. Roshan will be a bit late, he said. So we're waiting for Nobo. So let me just recall the last class. Uh, this is stuck. Okay, yeah. All right. So we were talking about differential forms on a manifold, right? And we defined integration of a differential form over a singular k cube, right? And so we saw that a differential form is determined by its integrals over k cubes, right? Because if I took a point P in the manifold and tangent vectors v1 to vk at P, then of then if I choose any singular k cube C, which maps the origin to P and whose derivative at the origin maps the basis vectors EI to the given vectors Vi in the tangent space, then if I use C to define a family of shrinking cubes, so I look at the cube C epsilon of x is C of epsilon x. In other words, I'm restricting C to a small cube of side length epsilon. And then if I integrate omega over C epsilon, so C epsilon, you see the sides are going to be more and more approximated by these vectors V1 to Vk. So what we found is that if you integrate over these shrinking cubes, then the limit of the integrals of omega over the C epsilon divided by epsilon to the k, this converges to omega at P applied to the vectors V1 to Vk, right? So therefore, the value of omega on any tangent vectors is given as a limit of integrals of omega over shrinking cubes with sides which are tangent to those vectors, right? And using this, it follows immediately that if the integral of omega over all k cubes is 0, then this right hand side, the integral over any C epsilon will be 0. So this limit will be 0. So that means omega acting on any k tangent vectors V1 to Vk will be 0. So omega will be identically 0. Okay, so therefore, the integral of omega over all k cubes is 0 if and only if omega is 0. So we'll use this fact a few times today. So this you can think of as saying that I have a linear map phi from the space of k forms omega kn to the dual of the space of k chains. Omega maps to the linear functional on k chains, which sends a k chain sigma to the integral of omega over sigma. Right. So this linear map is 1-to-1 because its kernel is 0. Right. Because if omega is in the kernel, that means that the integral of omega over every sigma is 0. So then we know that omega is 0. Right? So this map is injective. So that means the K forms are, you can identify with a subspace of the dual of the K chains, which is called the cochains. Okay. So any questions? Okay. So so at the end of last time, we had this question that we defined this boundary operator from K plus 1 chains, K chains. So this is a linear map between vector spaces. So there is a dual linear map, delta star, between the dual spaces from K cochains to K plus 1 cochains. And now sitting inside the K cochains, we have the K forms. And sitting inside the K plus 1 cochains, we have the K plus 1 forms. So the natural question is, does the dual of the boundary operator map this subspace of K forms to the subspace of K plus 1 forms? Okay. So we're going to give an answer to this question today. And the answer will be yes. And it will be in terms of something called a differential operator on forms called the exterior derivative. So is everyone familiar with the exterior derivative in Rn? Yes?
Needs recalling.
Sorry?
So recall just here.
Yeah, I'll recall the formula, of course. I'll recall. Okay. So we have M is a smooth manifold. And suppose I have omega is a K form. One second. This is going a bit slowly. Let me just turn it. Okay. Omega is a K form. And suppose I take a chart, all right? So phi equal to x1 to xn from u in n to v in Rn is a chart. So so this is u, and this is phi. X1 to xn. And this is v in Rn. This is u in n. So on this chart, omega I can write in terms of dx size. So let me write it as a sum over multi-indexes I bar. A bar of, so these will, I write these as functions of the coordinates x, okay? So A bar of x, dx I bar. Okay, so here, if I bar is a multi-index I1 to Ik, where 1 less than or equal to I1 less than Ik less than or equal to n. Okay, then we'll use the notation dx I bar will be dx I1 wedge dx I2 up to dx Ik. Okay. This is just a compact notation, all right? So any omega we can write in terms of these dx I bars, right? So what does it mean to say that omega is summation ai of x dx I bar? It means that if I take here the form omega tilde, which in Rn is given by the same formula, ai of x bar, sorry, ai of x, ai bar of x, dx I bar, then this means nothing but omega is equal to phi star the pullback of omega tilde, right? Is this clear?
Yes.
Okay. Now in Rn we have this differential operator, the exterior derivative. So this omega tilde is a differential form on V in Rn. So here we have a k plus 1 form d omega tilde. This is defined to be the sum over I bar d of ai bar wedge dx I bar. Okay, so this will be a k plus 1 form. All right. Okay. So now what we want to do is we want to define the same k plus 1 form in the manifold, and we want to call that d omega. But a priori, this might depend on the choice of chart. Okay, so we define let me call it d sub phi of omega. So to indicate the dependence on the chart, this will be summation over I bar d ai bar of x wedge dx I bar. Okay, so this will be what? This will be phi star of d omega tilde, right? Okay. Yes.
Yes, sir.
Yes, sir.
Right. Okay. So what we want to do is show that this is independent of the choice of charts. So we've used charts to define this exterior derivative of omega. Now we're going to show that this is independent of the choice of charts. Okay. So to do that, we're going to use singular k cubes. So suppose I have a singular k cube now C, which takes values inside this chart U. Okay, so this is C going from 0, 1 to the K into the manifold, into the chart U. And so then if I compose this with my chart phi, then I will get a singular K cube in Rn. Let me call that C tilde. So this is phi composed with C. So this will map into Rn. Okay. Now I want to use the fact that we have Stokes theorem for chains in Rn and differential forms in Rn. Okay. For so by Stokes theorem for chains in Rn the integral of so suppose this is a k plus 1 form, sorry, not a k1. This is a C is a k plus 1 cube, sorry. This is a k plus 1 cube. So the integral over C tilde of d omega tilde is equal to the integral over the boundary of C tilde of omega tilde, right? Yes, this is Stokes for chains in Rn. Yes?
Yes, sir.
Okay. But now what is this first, the left-hand side? Now the integral over C tilde of d omega tilde, this is equal to, what is C tilde? This is phi composed with C, right? So this is integral of d omega tilde over phi composed with C. So this will be the integral over 0, 1 to the k of, so I have to pull back by phi composed with C. That is the same as the pullback by C star of phi star of d omega tilde, right? Yes?
Yes.
So this is the pullback of C star of phi star d omega tilde is what we're defining to be d phi omega, right? This is d phi omega. So in other words, this is the integral over C of d phi omega, right?
Right.
Okay. But now similarly, if I look at the integral of omega tilde over boundary C tilde, boundary C tilde is a sum of faces of C tilde. Now faces of C tilde will be given by composing faces of C with phi, right? So so what I mean is, since
Sir, it will be k plus 1.
Sorry?
In the last line, it should be k plus 1, right?
Yes, thank you. Yes. Thank you. Yes. So since C tilde, the I alpha face is equal to phi composed with the I alpha face of C, okay, we have that well, and omega is equal to phi star omega tilde. Okay, so similarly we have that integral of omega tilde over boundary C tilde will be equal to the integral of omega over boundary C. Is this clear? Okay. So thus we get that the integral of this d phi omega over C is equal to the integral over boundary C of omega. All right. Yes.
Yes.
So this is for all singular k plus 1 cubes C such that image of C is contained inside U. All right. So Stokes' theorem holds for this exterior derivative in the manifold for cubes which are contained inside the chart, right? Now using this, we can show that this d phi omega, this is actually independent of phi of the chart or the choice of chart phi. How? Because now given P in U and k plus 1 tangent vectors v1 to vk plus 1 in TPM, you let C from 0, 1 to the k plus 1 to M be a singular k cube such that C of 0 is P and DC0 of EI is VI for all I between 1 to k plus 1. Okay. Then we know that d phi omega at P of V1 to Vk plus 1, this is the limit epsilon tends to 0, 1 over epsilon to the k plus 1, integral over C epsilon of d phi omega. Yes, we know this.
Yes, we know this.
Right, and just notice that for epsilon small, because P is an open set and C0 belongs to P, so C epsilon, the image will be contained inside U for all epsilon small, right?
Right.
Okay, so this is well defined. This makes sense. So note image C epsilon contained in U for all epsilon small enough. So now we can use Stokes' theorem for these chains which are contained inside U. So this becomes an integral 1 over epsilon to the k plus 1 integral over boundary C epsilon of omega, right? Okay. Yes. Okay.
Yes.
Now this last quantity is independent of the chart phi, right? This limit, this only depends on omega. This is independent of the chart phi. I'm not using the chart anywhere now, right? Is it clear? Therefore, this d phi omega is independent of the chart phi. Is it clear? Yes?
Yes. Yes, sir. Yes.
Okay, so this is independent of chart phi. Okay. So thus d phi omega is independent of choice of chart phi And so we obtain definition the exterior derivative so this will be a map from K forms to K plus 1 forms. So this is defined by locally if omega equal to summation over I bar ai bar dx I bar, then d omega is equal to sum over I bar dA I bar wedge dx I bar. Okay. All right.
Yes, sir.
Now, notice something that we so this is well defined. This is a well defined differential operator from K forms to K plus 1 forms. And note if omega tilde is equal to the same sum over I bar ai bar dx I bar in Rn, then d omega is phi star of d omega tilde. Okay. So if I look at d of d omega, d of d omega, then this by definition, this will be phi star of d of d omega tilde, right? Yes. Okay.
Okay.
Right. But this will be phi star of 0, which is 0, because d of d omega tilde is 0 in Rn. This we know for the exterior derivative in Rn, right? Okay. Is this clear?
Yes, sir.
Yeah. So the exterior derivative also satisfies that d of d omega is 0. Okay. So d squared is 0, in other words, d squared is 0. Okay. So d squared is 0. Okay. So we define then omega in omega km is closed if d omega is 0 and exact if omega is d alpha for some k minus 1 form alpha. Okay. So then it's clear that the closed forms, they form a subspace of the space of K forms, and the exact forms forms the subspace of the space of closed forms, because d of omega will become d of d alpha, which is 0, right? So any exact form is closed. So we can define the de Rham cohomology H upper K de Rham of M. This is defined to be the space of closed forms modulo the exact forms. Okay. All right. And it turns out this is a topological invariant of the manifold. It looks like it depends on the smooth structure, but actually you can show this is isomorphic to the kth singular cohomology with real coefficients as a vector space over R, and that is a topological invariant. So, okay. So anyway, that's de Rham's theorem. I won't go into that, but I just wanted to make this definition for you. So we also have the following theorem, which is Stokes for chains in a manifold. So if omega is a K form and C is a singular K plus 1 cube in M, then the integral of d omega over C is the integral of omega over boundary C. Okay. So we prove this when the image of C lies in a chart, right? Then we know this. So yes, by definition of the exterior derivative, I mean, we showed this when the image of C lies in a chart, this is true, right? So this holds if image C lies in a chart. Yes?
Yes.
Okay, for general case, what you do is you look at basically 0, 1 to the K plus 1. And you divide this into small cubes. Okay. And for general, so here you have C. So this will be the image of C. So the image of C is compact. So it's covered by finitely many charts. So this is image C contained in M. For general case, cover image C by finitely many charts UI. So this gives me a covering. Let me call this script U. And then we have the Lebesgue number of this covering. Right, my manifold I can assume is a metric space. I can choose a Riemannian metric on it, and then it becomes a metric space. And so this finitely many charts, this has a Lebesgue number. So using the Lebesgue number of the covering U, and the uniform continuity of the map C, right? There exists a large integer n such that if we divide this k cube into small cubes, this k plus 1 cubes into small cubes of side length 1 by capital N, right? Such that, so dividing zero one to the k plus 1 into n power k plus 1 small cubes, image of each cube under C is contained in some UI. Right, this we can do, yes. Okay, so if I take one small cube here, then the image will be contained in some UI. Okay. Yes.
Yes.
Now you let